Welcome back, folks. I'm recording this series of videos because I find that a lot of students need a little bit of a refresher on complex numbers and why they're important. I find a lot of variation in how it was taught, whether you took it in high school or if you took it at when you got to the university or anything like that. There's just the level of knowledge is all over the map. So I want to record this series of videos. If you need the help, if you need to go back and review a little bit, I find this to be valuable. So I think it's important. Okay. So complex numbers, everybody kind of has their own ideas. I usually ask in class and I say, well, what's an imaginary number? And everybody goes, well, I. Yeah, it's I. And what's important about I? Square root of -1. And I go, yeah, that's true, but it's really not the most important thing. And it's not what's important about complex numbers. So we kind of have to look at what we're really representing with complex numbers and how they relate to the stuff we learned in grade school. The first thing you learned about numbers was probably how to count. Like you sat there and you did 1, 2, 3, 4. At some point you might have learned what 0 is. How much broccoli do you want to eat? 0. 0 broccoli. Eat your vegetables. And then, deeper into your schooling, you might have realized that there were numbers that are less than 0, like -1, -2, -3, -4, so on and so forth. All of these numbers, what they are doing is allowing you to locate a point on a number line. Okay? And all of these numbers accomplish two things. They tell you how many steps away from, like steps or units away from the origin, and that's indicated by the magnitude of the number, right? The bigger the number, the further away from the origin you are. And the other thing that's indicated is the direction from the origin, okay? And that's indicated by the sign. Positive you go one way, negative you go the other. So let's take a peek at that, and I have that down on the notes there. So you get distance from the origin and you get direction from the origin. Those are the two things that we're representing with a number, and we start out doing this on a number line, right? So if you have +2, let me see if I can copy this over here. If you have +2, you might represent it on a number line as this vector. It starts at 0 and it points over here to 2. Okay, that's +2. So you get distance and direction in that way. You can play the same game with -3. Okay, you might say, hey, that's -3. Okay, the negative tells us we're going to the left, and 3 tells us how far we're going. Okay, this is what numbers are doing. Complex and imaginary numbers do the same stuff. Okay, the only difference is that we're locating this point in space, okay, the tip of wherever the arrow is, we're locating it in 2 dimensions instead of 1 dimension. So I think that imaginary numbers is a horrible name for these 2-dimensional values. I think complex numbers, it's a little better, but it can still be a little off-putting, like, oh, it's complex, I can't understand that. And you can, okay? I want you to think of them in your head. They're just 2-dimensional numbers. We're just locating a point somewhere off the number line. Like, what if I want to come up here and locate a point? Or what if I want to come down here and locate a point? How do I represent that? And I can't represent that with just an integer. So we need to change the way we represent numbers, and we do that with complex numbers. One of the old mathematicians, I got to remember who it was, wanted to call them lateral numbers. I think that's a much better name for it. I kind of wish lateral numbers had caught on. Okay, so we still have that number line, right? I can still find -3, just like I did up there. Or I can find +2. Okay, so let's say this is +2, right? And this is -3 over here. But what do I do with this orange one? How do I locate that point now that I have this 2-dimensional area? And there's a couple ways to do it, okay? But we need the distance from the origin and we need the direction. Those are kind of the two important things that we're going to dig into. Okay, so that's the task of first starting out with complex numbers. And imaginary numbers are just a part of that, right? Imaginary numbers give us this direction, and real numbers give us this direction. Okay, so there's three forms that we need to look at when we're talking about complex numbers. And as long as each of these forms locates the same point, then they're considered equal. Okay, so let's pick a point in space, and it's a good one. Okay, and let's figure out how we can represent it. So let's say, how do we represent this point in space? I think that's worth writing. Okay, how do we represent a point? And we can say on a 2D plane, okay, but since we're going to represent it with complex numbers, we call this the complex plane. Okay, so I'm going to give you three different ways to locate that point. If you didn't know where I was talking about, you can look at the number, you can draw that point on this graph. Okay, so let's see here. What's my first form? The one that you're probably most comfortable with is called rectangular form. Okay, so we can say rectangular form. You have to figure out how to get from the origin to that point. And the way we do that is to break up the number. Okay, so we might say, how far along the real axis are we? And how far along the imaginary axis are we? Okay, so we might say, hey, if I want to get to that point, I can take +4 steps along the real axis. Okay, so that's going to be 4. Okay, we can even write plus in there. All right, and then we say how many steps along the imaginary axis. Okay, so we're going up here. That's almost a straight line. Let's pretend. Okay, and that's plus. And we went up 3, and I'm going to use J because I'm an electrical engineer, and lowercase I is current to me, so we use J for all of this, just to muddy the waters a little bit more. Okay, and we can say, well, hey, we took +4 and plus J3, and that's my number. And that point is really the end of a vector that looks like this. Okay, so we get our rectangular form that way. Let me get the +4 down here. Okay, so I get direction and distance, but I break it into 2 parts that are orthogonal to each other. All right, so that's rectangular form. We get distance and we get direction. The other one that I think is kind of more pertinent to what we do, but I find that it wasn't covered as well. And a lot of times you go learn rectangular form, and that's all you learn. And you walk in, and you've heard of polar form, but you're not as comfortable with it because you haven't used it a lot. Okay, all of these numbers, you don't use these on a daily basis. You don't pay for lunch using complex numbers. You don't figure out, you know, how much gas you're using in your car using complex numbers. So they're not as intuitive, right? So polar form's a good example of that. You're probably not comfortable with it yet. So I can find that same spot. Let me get this one up here. Okay, I can find that same spot on the 2-dimensional plane using a different method, but it still has the same pieces of information. It has distance from the origin and direction, but we do that a little differently. Okay, so we take the direction here, okay, and we'll find that that is +5. Okay, and then we also take the angle here to get the direction. Okay, and we'll find that that is 36.86. I didn't want to risk it. I thought I remembered. Okay, and that's in degrees. So we write that together as 5 at an angle of 36.86 degrees. Okay, gets me to the same point. And if it gets me to the same point, I get to say that those two numbers are equal to each other. All right, so we can do this. Just like that. Now, if you want to convert between them, do a little trigonometry. Right? That's all it takes is a little bit of trigonometry to get you where you're going. Okay? So we'll do that in a moment. But I want to cover one more form. And this form is, you know, chances are you haven't seen it at all. Maybe you have. But it shows up in a lot of the math that you'll continue on to do in electrical engineering. And your calculator will definitely use this form. You don't have to use this on every calculator. But you TI-84 folks, this is going to be your go-to. And MATLAB's going to use it. Okay, so it's important in that respect. And it's very similar to polar form. Okay, it has the same information as polar form. So let's get a fresh image down here and let's look at exponential form. Okay, exponential form uses the same distance out here, right? Okay, distance from the origin, just like before. So that was plus 5. And then it also uses this angle. It's just written in a slightly different way. And if we're being mathematically rigorous, which only happens occasionally, this should be in radians. Okay, so instead of 36.86 degrees, it's 0.643 radians. Okay, and that's in radians. So putting this together, the form looks like this. It's 5 times the natural constant e, okay? So 5e, and it's raised to a complex number, okay? 5ej 0.643. And it's similar to polar in that it has the magnitude of the vector, right? Just the length directly to the point. And it has the direction as an angle, but it's in radians. Now, we'll get sloppy. I promise you we'll get sloppy. But we can, for now we can do this, right? We can say that these two things are equal to each other. Okay? You will run into occasionally this, which is not mathematically rigorous, but gets the job done. Okay, just make sure you have your degrees marked there. Okay. So this is bad math. But used sometimes. Okay. Those are 3 ways we can represent those numbers. Okay, as long as we get to the same point on the complex plane, they're all equivalent to each other. Okay, so what do I want to do? What do I want to do? I'll do a quick video on converting between the forms. It's really just a right triangle with a little bit of trigonometry, and then we'll jump into what I think is important about complex numbers and how they relate to the simple 1, 2, 3, 4, 5, scalar values that we learned to count with and do operations on as a kid. All right, so conversions next, and then jumping into operations.